Coming up in this edition, it's not every day that millions of dollars worth of aeronautic equipment is sent crashing to the ground on purpose. Find out exactly why NASA smashed these aircraft into the concrete and the technical legacy it provided for today's commercial craft. NASA searched for years for devices that could be used to bring astronauts and their spacecraft to a safe landing on Earth. Paraglider, parawing, gliding parachute and flexible wing. The basic design in all these can be seen in most hang gliders flying today. Look carefully and you can see that from underneath this plane appears different, very different. It's a design that couldn't be more radical, the oblique wing aircraft. It's a plane that travels further, faster and more efficiently than any that has ever proceeded. But first to our continuing story of Apollo 13. We left them last week with the ship back on track. Apollo 13's orbit would now take them behind the moon. But before that occurred, a key decision had to be made: where to bring them down. Their present course would take them to the Indian Ocean, where recovery would be difficult. A burn to bring them home quicker would take them to the Pacific Ocean and nearer to recovery forces. Bringing them home even faster would place them in the South Atlantic, again away from recovery forces. It was decided to take them to the Pacific. Apollo 13 passed within 137 miles of the moon. For Lovell, it was the second time he'd been so close to the target destination. There was no time for contemplation. There was another critical burn coming. As the distant voices crackled across the airways to Houston, the world's press gathered to tell the story. Shortly after Apollo 13 had separated from the Saturn third stage, the stage had been sent on a trajectory toward the moon. Its impact would be recorded by the seismometer left by Apollo 12. The impact was successfully recorded, and the ground-based scientists telling the astronauts that the force of the impact appeared to be substantial. To conserve the electrical power and cooling water, the crew shut down all but the vital life-sustaining systems of the LEM. Flight Director Eugene Kranz was now cautiously confident that the lunar module was fully capable of getting the crew back. As he pointed out to newsmen at the time, the module, or LEM as the world quickly began to know it, had always done more in tests than was expected of it, and now that performance record was good news for the safe return of the astronauts. On board, not everything went entirely to plan. The water gun was leaking, and although it was quickly shut off, Lovell estimated it had lost about a quart of water. The people of the world, of whatever nationality, were now becoming absorbed by the life and death drama in space. Space professionals were loud in their acclaim of the positive and competent attitudes displayed by the astronauts. However, the crew then faced another problem: their own exhaled breath. The lithium hydroxide chemical to take carbon dioxide out of the air was not sufficient in the lunar module. Ground engineers improvised and discovered that the canisters from the command module could be adapted to fit the hoses in the LEM. On the ground, an adapter was fashioned for materials that the engineers knew would be available to the crew aboard the LEM: cardboard, plastic bags and tape. After checking out the effectiveness of the instant invention, construction details were sent up to Aquarius. The astronauts were able to put together 2 of the makeshift devices, and within an hour they noted a marked decrease in carbon dioxide. After a small burn to correct the course of their trajectory, the crew jettisoned the damaged service module. As the module floated away, the astronauts were amazed to see that a whole side of the module appeared to have been blown away. Now it was time to clamber back into Odyssey to jettison Aquarius prior to re-entry back into the atmosphere. Lovell's emotional words were heard in Mission Control: "Farewell Aquarius and thank you." Lovell, Swigert and Hayes were now on the final leg of their life-threatening journey. But to add to their difficulties, they were all exhausted, relying more and more on the support, both technical and mental, of the ground crew. All the while, the world came to a standstill to watch this human drama unfold. From the first news of the accident through to the final tense moments of the re-entry blackout and the worries about the effectiveness of the heat shield, people all over the world followed the story on radio, television and in the papers. For 4 days it seemed everyone watched and waited to see if the crew would make it back safely. During the emergency, the astronauts were unaware of all the attention being given to their situation. They were focused entirely on the task of getting their crippled spacecraft home. The tension in Houston was palpable during the re-entry blackout.
Odyssey Houston, standing by, over.
And then the staccato voices of the astronauts were followed by a visual sighting on the giant TV screen in the Mission Control Center, as the ground staff stood as one to applaud the return of the three spacemen. On the 17th of April 1970, at 7 minutes and 44 seconds past midday Central Standard Time, the crew of Apollo 13 splashed down, only 4 miles from the prime recovery ship, the USS Iwo Jima. The astronauts' relief was shared by anxious viewers the world over, with tears shed and spontaneous applause breaking out wherever the splashdown could be seen. The world's press rushed into print to spread the good news. It was 2 months before NASA was satisfied that the reasons were understood. The accident began, in fact, in 1965 when the design engineers decided to change the spacecraft power supplies from 28 to 65 volts. Normally, of course, such a change would cause a cascade of other changes as designers adapted their particular components to the new operating environment. However, the people building the innards of the service module oxygen tanks somehow never became consciously aware of the change. Each of the tanks contained a stirring fan, a heating element, and a temperature-sensitive switch designed to shut everything off if the element got hotter than about 25 degrees centigrade. And none of these components was ever redesigned to accommodate the higher voltage. But with the safe return of the astronauts, the faces at Houston that had been creased for days with tension were now creased with smiles. Lovell, Swigert and Hayes were accorded a hero's welcome, with President Nixon one of the first on the telephone to congratulate them on their safe return. Nixon went on to say that, while some may claim the aborted flight to have been unsuccessful, he would declare it a successful mission. From the start, the President pointed out, the exploration of space has been a hazardous adventure, and the voyage of Apollo 13 had dramatized its risks. But, he told the astronauts, their mission had served their country. It had served to remind everyone of the proud heritage of their nation, to remind all that in this age of technicians and scientific marvels, that the individual still counts, and that in a crisis, the character of a man or woman will make the difference. Today, the safety record of light aircraft is at its peak, but it hasn't always been that way. As recently as 2 decades ago, hundreds of small plane crashes accounted for thousands of fatalities annually. At the same time, there was no method of predicting the behavior of general aviation planes when they crashed. So, in a joint project with America's Federal Aviation Authority, NASA began a light aircraft crash safety program at the Langley Research Center in Virginia. This was one of 20 flood-damaged planes that was to be tested. The actual facility was originally used by Apollo astronauts to practice landing on the moon. The 80-meter high by 130-meter long lunar landing practice area was laced with cables that were attached to the highly instrumented aircraft before it would come crashing to the ground. Dummies riding in the passenger seats were also instrumented to measure G-forces. Engineers hope to learn what happens to an airframe structure when it impacts, and to develop an analytical design tool that could be turned over to the designers and builders of general aviation planes. For this first checkout test, the plane was complete except for tail section and engines. Comparable weights took the place of missing parts, and the fuel tanks were filled with water for weight and balance. This first crash was made at an impact speed of 50 kilometers per hour. Future drops were at speeds of up to 100 kilometers per hour. Here you can see some of the resulting damage, most of which was confined to the nose and underside of the aircraft. The proposition at the time was that the test would lead to the integration of energy absorption concepts into airframe design. And that is exactly what happened. And planes weren't the only things they were dropping on purpose at the Langley Research Center. In this case, it was a 1.2-ton Army helicopter. The CH-47 helicopter had earlier been damaged by fire in the plant where it was manufactured, making it a good candidate for the crash worthiness test. Watch again, this time in slow motion, as the helicopter was dropped 20 meters to the concrete below. The highly instrumented craft was being used in a cooperative experiment with the U.S. Army to improve design and safety features of future helicopters. Crash worthiness tests of both helicopters and planes has improved aircraft design and ultimately saved many thousands of lives. Hang gliding is as close to the birds as most of us will ever get. This is the man responsible for co-inventing the specially designed wing that made hang gliding such a rapidly growing sport. 63-year-old aeronautic engineer Francis Rogallo. Now retired from NASA's Langley Research Center in Hampton, Rogallo enjoys flying a couple of times a week at what's been called the highest sand dune on the East Coast, Jockey Ridge. Rogallo enjoys the novelty of taking to the air and the freeness of the movements allowed by the glider, both side to side and up and down. Big kites were a labor of love for Rogallo and represented more than 2 decades of research, much of which was done on his own time. And for their remarkable efforts in 1963, he and his wife received from NASA one of the highest cash awards ever given for an invention. Experimenting with small gliders and kites, a fully performing and completely flexible wing finally evolved in 1948. Ten years later, NASA was searching for devices that could be used to bring astronauts and their spacecraft to a safe landing on Earth. Early versions had many names, including paraglider, parawing, gliding parachute, and flexible wing. The basic design in all these can be seen in most hang gliders flying today. Intensive testing ranged all the way from small wind tunnel models to full-scale flight tests complete with manned spacecraft attached. While the Rogallo wing, as it's known by many, has had limited applications outside of sport, Rogallo himself is optimistic. Interest generated by many thousands of flyers around the world will produce other applications in time. The scene was an arid lake bed at NASA's Dryden Flight Research Center near the Mojave Desert in California. It was early morning. Engineers and technicians were there since before sunrise. Checkup and preparations for the upcoming flight test were painstaking and deliberate. This is not an ordinary plane. It has a unique scissor-like design. Studies indicated that if the design features of the oblique wing, as this 25-foot model is called, were applied to full-size jets, it would allow them to travel faster than sound without leaving the usual sonic boom in their wake. Additionally, it would give them increased fuel economy. Before the oblique wing plane took off, a television-equipped aircraft swept over and scanned the flight path. What the camera saw aided this man, the pilot of the oblique wing model. He actually flew the plane from inside this van. Another television camera mounted in the nose of the test aircraft let him see where the plane was going. The ground crew was responsible for starting the engine and launching the oblique wing plane. During the flight, researchers carefully recorded how the aircraft responded to a number of maneuvers. They compared these responses with wind tunnel predictions to better understand what the aircraft was doing and why it was doing it. Research showed that the oblique-wing aircraft, compared to fixed-wing planes, used less fuel and could reduce sonic boom levels. The plane's designer, R.T. Jones, said that using the oblique wing took maximum advantage of wing sweep in a way that fools the wind, by making it think the plane is traveling slower than it actually is. The next phase of research involved a manned and jet-powered plane. These artist concepts show how the oblique wing design might have been applied to transport-type aircraft. The wing, of course, would swing back to a more conventional position for landing. The oblique wing is a unique design that allows planes to fly faster, quieter, and to use less fuel. Ever seen a jet plane fly underwater? Well, this model of a 747 almost does just that. But consider first what led to these interesting underwater studies. NASA researchers were trying to solve the problem of wing vortices, those funnel-like patterns of air that swirl off the wings of planes as they speed along. The larger the plane, the larger the vortex and resulting problems. Vortices can't be seen unless smoke or dipods are attached to the wings. Here, the second test plane intentionally followed much closer than normal. This allowed designers to visually observe and study both the vortex and its results. Air traffic controllers can avoid the problem altogether by carefully spacing takeoffs and landings. But researchers knew if the vortices could be reduced or eliminated, it would reduce air traffic delays and fuel consumption. This is Aeronautics in Laurel, Maryland. It was here that NASA completed a series of tests to look at the vortex problem from a different angle, underwater. The tank used was 140 meters long, 10 meters wide, and 11 meters deep. The advantage of using water was that researchers could simulate much closer the physical behavior of a vortex, but on a small scale. A second model was used on a separate carriage that followed the first, to simulate a light aircraft in the wake of a larger one. This test lasted approximately 25 seconds, from which 15 seconds of usable data was gathered each time. As the test progressed, dye was released from the wings of the so-called generator model. Using this technique, researchers could visualize the actual vortices as well as capturing them on film for later study and analysis. The novelty of the test tank and the groundbreaking nature of the oblique-wing aircraft are the types of innovation that have put NASA at the forefront of advanced aircraft research and design. That brings us to the end of this edition. We look forward to your company next time, and once again we'll take you above and beyond.